Okay, we're gonna go back to where we left off. I'm glad that I took a look because I actually found an easier way for us to go. So I think you'll appreciate that. Okay, so we're gonna go ahead and do a little simplifying here. And we're gonna rewrite. We notice that what's left here is -2 to the first power. This becomes n plus 2. If I compare these, x minus 1. And that's all over n plus 1. Alright, now anything that does not involve n gets pulled out front. So that means the absolute value of -2 times x minus 1 times the limit as n goes to infinity of the absolute value of n plus 2 over n plus 1. So this limit is infinity over infinity, do L'Hopital. We can see that this goes to 1. So we have the absolute value, let's distribute, minus 2x plus 2 times 1. It's got to be less than 1 for convergence. So that means we have to solve this inequality. And if I start to play around with it, I remove the absolute value signs, and we have to get x by itself. So we're going to subtract 2 from everything. So we get minus 3 is less than minus 2x is less than minus 1. Now here's the key step. Getting x by itself, we're dividing by a negative number. And remember what happens when you divide by a negative number. You flip the sign. So this becomes 3/2 is greater than x is greater than 1/2. Or you could write it, we usually write things the other way from lowest to highest. And just check the mouth. Make sure the mouth is pointing in the right direction. Okay, so now we're going to keep moving on. We got to test those endpoints. So the first endpoint we're going to check is 1/2. So we're going to test endpoint x equals 1/2. So we take 1/2, we put it into our original equation. Or series, excuse me. So this becomes minus 2 to the n plus 1, and 1/2 minus 1 to the n power. So this is equal to the series minus 2 to the n plus 1 minus 1/2 to the n. We can group these together because they're just constants for every increment of n. So this becomes minus 2 times minus 1/2 to the n plus 1. And simplifying this expression becomes 1 to the n. And 1 to the n is just 1. So by the nth term test, we know that this series diverges. So we do not converge at that endpoint. Now we're going to test the other endpoint. So we're going to test x equals minus 1/2, or I'm sorry, 3/2, x equals 3/2. So we're going to take 3/2 and put it in our original series. And this becomes minus 2 to the n plus 1, and this time we have 3/2 minus 1 to the n. And simplifying, we have minus 2 to the n plus 1, then we have 1/2 to the n. So just like before, we're going to group these together, and we're going to get minus 2 times 1/2 to the n times n plus 1, which leaves us with minus 1 to the n plus 1. So now we know that we have an alternating series and we need to use Leibniz. So we have alternating series, Leibniz. So we need to do 1, 2, 3, and then we need to check if we're conditionally convergent. So 1, 2, 3. So my use of n is just the n plus 1. All the use of n's are positive, so check for that. Now, is use of n plus 1 less than or equal to u sub n? Well, that answer is no, because these terms are growing, not shrinking. So we fail here. That means we're divergent at that endpoint. So we're actually divergent at both endpoints. So in conclusion, our interval of convergence is 1/2 is less than x is less than 3/2. We converge absolutely on that same interval of convergence, and we converge conditionally nowhere. And that's our last example. Thank you.